his old hand around here. He's interested in the presentation on DCF because he developed, for instance, the code that Steve Pilgrim is now adapting to this. Was also a part of the team that tested the DCF, the original DCF, I suppose, when you were involved in it. Anybody has anything else to discuss before we go to the presentation?
Alrighty, so thank you to Dr. Sabo for coming to today's meeting. So we'll begin. So ostensibly, today's presentation is about continuation of work on the diverging Cusped thruster class that was established a few years ago by Dan Courtney. And we've been continuing work on it and trying to understand the basic physics of this thruster in order to come up with a more efficient, less corrosive model. So with that in mind, we want to adapt what we've learned from the DCFT, create a new thruster, ostensibly for use on upcoming work on plasma material interactions that we are engaging with at the fusion department. So in this presentation, I'm going to go through the methodology that I went through in order to actually create this new thruster. A lot of lessons learned from the DCFT model, as well as work done by a Europe named Joe Conti, who also performed work last summer and came up with his own design. So in the process, I had to consider the most important aspect of the DCFT, which is the magnetic topography, which really decided ionization factors, containment of electrons, etc., which all are critical aspects of Hall thrusters, and in our case, diverging Cusped thrusters. So the objectives I pretty much outlined here, and this is still an ongoing project. We've come up with a viable design, but we still have to build and test these designs to see if our efforts have been successful. So just a background for folks who don't know much about DCFT. It's similar to a Hall thruster in many aspects, but there are key aspects that are quite different. For instance, it's not cylindrical. The diverging part probably tells you that aspect right offhand. We use a permanent ring magnets, samarium cobalt grade 3212 for our magnetic fields, and we have them alternating. And basically alternate polarity, and we create these cusps, hence diverging Cusped thruster. We also have basically, you can see over here, the design of our DCFT. And as I said earlier, the idea is we want to create this design to determine the effects of magnetic topography. So Steve and Taylor have been working on this for the last few years, and yes, we have actually done computational work and also erosion studies at the Air Force Research Lab, where we determined that erosions are taking place at the cusp and also at the exit as well. Another important aspect that they determined from their work is that there's a creation of an oscillatory high frequency, high current mode, which is not very beneficial for the erosion and efficiency of the thruster. So in addressing this, Joe was tasked last summer to come up with a new design which would take the lessons learned from DCFT and come up with something that's better, so to speak. So these are all aspects that are very critical for the new design that he had in mind, and what I had in mind when I came up with alternate thruster design to it as well. So the idea is of having a field line coming outside the plume, ending in the downstream cusp. That's critical to having a cathode location and also eliminate the worries of cathode erosion. The other aspect is the high field strength and gradients at the cusp and the anode. It's also taking advantage of the magnetic mirroring that will help trap the electrons and help with ionization, also prevent the electrons from going to the anode. Lastly, you want to have low field strength outside the mouth of the thruster so that you have electrons coming in, and you have a flat downstream separatrix, which I'll elaborate in a moment. The aspects I brought into this design, which is different from what Joe had, was a more modular aspect of the design and a far more cheaper design. Because one driving factor in this particular design that I had in mind was to have a cheaper thruster in order to facilitate construction, because the original design that Joe had was around $7,000. I have a design constraint of $1,500 or less. And that was a very interesting challenge, so to speak, and I addressed it in several ways, as you see. what I mentioned earlier about the flat separatrix issue. The original design for the DCFT, you probably can't see well because of the color contrast here, is that you had these cusps here, and you also have these separatrixes between these cusps. Well, as you can see, these cusps don't have flat separatrixes. So what's so important about these separatrixes? So the importance is due to the fact that you have your ions going out perpendicular to the plane of these separatrixes. So if you don't have a flat one, so you have a spreading path for these ions, which is not optimal for performance. If you have a flat one, flat perpendicular to the surface and flat, parallel to the path of the flow, then you would have optimal performance because you have the ions coming out directly in the path of the flow. So essentially, flat separatrix was a high priority in our design. I mentioned earlier about not having a divergent geometry for this design. There's also critical aspects of the density of the electrons. So we determined that if you have a cylindrical design again, you might be able to have low non-oscillatory currents, which would be beneficial for efficiency and for erosion issues. So moving on. This is the original budget for the original DCFT, and it was around $3,000. The critical aspects of the design, which were very costly, were really the magnetic circuit assembly, which was mainly the samarium cobalt magnets, and also for the inserts, the insulator cone, which is boron nitride. And I tried to address both issues, trying to mitigate the cost factors in two ways. One, we tried to have more standardized ring magnets for the samarium cobalt magnets. If you have bevels or special designs for differing sizes, you have more costs. The other aspect why these magnets were previously so expensive is because we bought different sizes in small quantities. I thought if you had a standardized size, but you bought in bulk, you'd be able to drive the cost down drastically and facilitate cheaper design. The other aspect is the boron nitride, which we bought from Saint-Gobain. It was expensive because they machined the boron nitride instead of our own facilities doing it. So I thought, why don't we buy a block of boron nitride, follow standard procedures for machining it, which there are available online, and drive the cost down also in that fashion. So I was able to contact 32 different companies for samarium cobalt magnets, asking for different sizes, different configurations, buying bulk, buying etc. I was able to drive the cost down to around $109 per magnet if we buy it in quantities of 10 or more, which would be more than enough of a cost drop to make my original estimate $1,500 thruster an entirely impossible domain. For example, Joe's design was around $2,500 or $3,000 approximately. So just by the cost of the magnets, we were able to reduce it to a third. And based on the designs I have here, we actually don't use all 10 magnets, so actually it's probably much less than that. So the question is, how do we design these thrusters in the first place? So there's commercial software called Maxwell, which utilizes finite element method to actually calculate potential, calculate the magnetic fields based on magnets that you have. Oh, this is terrible, color-wise, because, okay. So essentially, the color was better from the projector. We would see the different materials and different color coding, which associates with the materials that we use. So this would be kind of complicated in subsequent slides, but I'll try to guide you guys onwards. So these are Maxwell simulations for the original DCFT, and also Joe's design, which has come up with last summer. One aspect of Joe's design, which also made it complicated, was that it was much larger than the original DCFT, in addition to being much more expensive. So you can't have very good comparisons between the two designs. So we tried to drive the size down back to the original DCFT configuration. And the subsequent slides for the subsequent prospective designs sort of reflect that. So essentially here, I'm trying to explain what these colors, well, this is supposed to be red, and that's supposed to be teal, and that's supposed to be purple, so it's kind of hard to differentiate in this projection. Several designs that we investigated, okay, that's even worse than the previous slide. But ostensibly, I'll try to explain what these plots would look like. So basically, you have the thruster design. You have an aluminum shell, which is not indistinguishable with the background here because of the projector, which would cover the majority of the thruster, and you have a series of alternating magnets with aluminum spacers. And as a result, you see there's a multiple cusp design. This is an initial design once I came up with the idea of using more magnets, but smaller magnets and cheaper magnets. So this original design came up with some interesting ideas to start off with, but this was not anywhere near the final idea. So progressing, we tried other ideas that are similar to how thruster designs are in the field right now, like at Princeton, etc. So we tried shielded designs where we have these magnets surrounded by iron primarily, and you have these flat separatrices for the design we have here. The only problem is that it's not as desirable because the design is still bigger than the DCFT design because of the bigger magnets, and because the exit separatrix is so deep within the thruster. So we tried to address these two aspects in the further designs by using these shorter magnets I described earlier. So again, you have, basically to get the thicker magnets, you have stacking magnets of the same orientation, which was very useful for making larger magnets with smaller magnets, but again, we still had the problem of not having optimal topography. We had weak field strengths, as you can see in this diagram, at the anode, which was not desirable. So moving on, we tried even more designs, and they were getting closer and closer, but there is still a discrepancy between the flat separatrix and the field strengths, which had to be addressed properly. So this was a design that showed some promise. We were able to drive the separatrix as near to the mouth of the thruster as possible, but we still had the issues of the weak field strengths. And we also had the issue of the thruster still not being a comparable size with Dan Courtney's design. So we went through several iterations with various different sizes for spacers, magnets, etc. And we eventually came to a design that had most of the aspects that we really desired for a design, which included that somewhat flat separatrix at the exit, and somewhat stronger field strength. Here you probably see a better gradient with better projection, but here's some plots that tell you a pretty good idea of the topography on this example. So you have this design where you have these three plots. So they're magnetic field strengths in units of Teslas. So on the top right, top left plot, you have magnetic field strength across the mouth of the thruster, where essentially that would be where the separatrix would be. You have a very, very, very weak field, like around 100 Gauss, which is both desirable and undesirable at the same time because, well, you have a weak field strength at the mouth, which is what we wanted in the first place. On the other hand, you also have a very, very weak field at the exit separatrix, at the exit cusp, which is not exactly the optimal design.
The center is to the right and the wall is to the left?
Yeah, so the wall would be the bottom. Yeah, so the mouth would be the top, the bottom right would be the wall, and the anode would be the bottom left.
I cannot read the number there. What's the number at the wall? Or
So,
the left?
top left, it's around 0.03 Teslas, so that's around 300 Gauss, yeah, which is fairly weak. But you did have relatively high field strength at the anode and at the cusp, which were pretty much what we desired. So we had the strong strength at the anode and the strong strength at the cusp inside, but the exit separatrix was pretty weak. So we tried to come up with this design, which is okay, but we don't know how good it would be. So we also came up with a repeating design, which is very, very similar to the original design came up by Giocanti, where we have a fairly strong strength at the mouth and a fairly strong strength at the anode and at the wall, and you also have the flat separatrix. The drawback to that design originally was that it was too big and it was too expensive, and the field strength was too strong at the mouth. So I tried to resize it appropriately so that it's actually at the size of the original DCFT. That's actually much cheaper than the original design, and incorporate the high field strength at the anode, at the wall, and at the mouth. And more or less, this is the design that Joe had, but adapted on a much smaller scale, and it's 1/6 of the cost. And the field strengths are similar to what we had earlier with the mouth, the wall, and anode. And basically, you can see at the mouth, the field strength is around 500 Gauss. The field strength.
You mean at the center or near the wall?
At the wall, it's around 500 Gauss. At the center, it's around 420 Gauss, more or less.
Yeah, those numbers cannot be read.
Yeah, the projection's pretty bad, unfortunately. So essentially, we have the design that Joe Conti had originally. It's on a much smaller scale and much more affordable. So we will build and construct both designs.
Well, that's not exactly true, right? Because Joe's outer cusp field was more like a few thousand Gauss.
It was like around 40. Oh, but this is the exit. Joe's few thousand Gauss was at exit separatrix.
Yeah.
That's away from the mouth.
Okay.
This plot was actually at the mouth.
I see. So what would it be at the separatrix?
0.45 Tesla, which is around 4,500 Gauss. So I was more concerned about the field strength at the mouth, but otherwise, it's pretty much very comparable to what Joe had. So it's basically the same design, except you don't have the beveled end, and you don't have the, it's also much smaller and cheaper.
Are you going to incorporate the bevel?
No.
Can it be done?
It can be done if we pay around $600 for a magnet, which would be far more expensive.
Or bevel only the non-magnetic material?
Yeah, we could chamfer it. That's not a problem at all. And that's actually a benefit of us machining our own boron nitride. We can make whatever configuration we want for the insert, and that can be easily be done in the next few weeks or months. So essentially, based on this presentation, we're going ahead with these two designs. One is basically a miniaturized version of what Joe had last summer, and the other one is a weak field strength at the mouth design that we came up with in the last few weeks or so. And we'll empirically build and test them and see how well they do. So essentially, these two designs met almost all of the criteria that we had in mind. The only difference between these two designs would be how strong the field is outside the mouth of the thruster. The ACFT has the low field strength that we wanted in the beginning to start off with. There are also some not cosmetic differences, but quantitative differences between the two. For instance, the ACFT has slightly weaker field strength at the anode compared to the miniaturized CFT. I believe it's around like 0.15 Teslas, whereas original DCFT had 0.3 Teslas at the anode, and the miniaturized CFT also has the same field strength there.
I know I always ask the same question, but
Sure.
in the design, the previous slide, you characterize how sensitive is the flatness of the separatrix of function of operating temperature, for example?
Yeah, there are SolidWorks thermal models which would correlate with how hot our duster could get, and so far they are well below the sensitivity issues with Samara and Ovo. Same thing with Joe's original design that he actually did some simulation work for.
That was not the question, right?
No.
I'm sorry. So.
No, I mean, you have a really flat surface in there, right? So my only concern is how sensitive is that flatness with the parameters that you select in your design, including operational parameters.
The flatness, I don't think, would be a function of the temperature.
So if you vary the strength of the magnet, it's going to continue being flat?
Yes, I think that's a plus.
Well, that's if you cool or heat them all really forward.
Which would not be the case for actual operations. So
So we don't know.
yeah, we don't know yet. But that's the issue.
I thought somebody did something on that. Was it Joe or somebody?
Joe did something, yeah. So how difficult, when you're playing with these models, how difficult is to get flat separators?
It was fairly well. Basically, I got some insight starting off from Steve actually. That's having a smaller magnet at the exit would help focus separatrix. So that is not that difficult. The only problem is that if you do that, then you drive the separations back from the mouth. And then you have the issue of eroding possibly corners of the thruster as it comes out. But alright, so based on the magnetic circuit assembly that I described just now, and also the cost of the boron nitride solid piece, we were able to get this cost estimate for both designs to around $1,000 for both designs, $1,200, which is well below what I originally projected for both designs. So success in that regard, I guess. So prospectively, based on what I've done so far, what we need to do in the long run, we have to continue fixing Astrovac so that we actually do the testing. We ordered the parts for both thrusters, and we have to commence construction in the next few weeks and months to come. Hopefully by June, we will have some fairly good data from Faraday Cup experiments, RPAs, etc. So we'll be able to quantify how well these thrusters would do, and basically justify or not justify the work that's been done now. So, questions?
I was wondering how you go about choosing like the number of cusps that you're gonna have, because I saw different designs with like more or less.
Originally, I wanted to go with something really novel, having a lot more cusps, but we also want to use a proper comparison against the original DCFT, so we stuck with 3 cusps, which is what they used originally.
And that number was out of thin air. I don't know.
It's pretty arbitrary, so we wanted to have some comparison, so we did 3 cusps again.
Yeah, because I was just wondering if, I mean, it seems like every set of cusps farther you go back, like fewer electrons are gonna get back on those, and you'll have less ionization back there. So,
Yeah.
but it just seems like just to compare to other designs. Okay.
Yeah, I think it's fair to say that the principal thing that we are trying to check is whether it is true that the convexness of the separatrix drives the divergence of the beam. That's a hypothesis that seems likely from what we know, but we haven't seen that. So by making it flat, is it true that now we have very low divergence? And then there are some more speculative questions about the whether that will drive a more stable operation, which is what the design at Stanford, like Capelli, has shown. So that is this guy, and it's very stable. We don't understand why. We want to test that as well. The number of cusps is another parameter. We just didn't touch it.
Okay.
The good part about this modular design is that we could disassemble the 2 designs I just came up with and possibly even play around with having more cusps and seeing what happens. So that could be an option that we could pursue in the far future after we do testing for these 2 designs.
I have a question. Do you have a name for it? Because it's not a divergent cusp field anymore.
That's actually something I've been struggling with, but we'll keep that as a work in progress. I like how Dan Courtney was able to incorporate his name into the design. I don't know if APFT is a viable option for that.
For the ACFT one, it looked like one of those spacers. Well, I guess for both of them, the spacer there is pretty thin. Is it? Did you do anything to check if that would actually saturate?
I did some saturation work after I talked to you about that, and it doesn't.
Why not?
No.
Do you have margin to make it thicker if it saturates?
Yeah, we could make it thicker.
Which one?
The spacer material we have here, the iron that we have, the 1018 steel.
That's the blue, right?
The teal color here. Well, here will be teal, but here it's more blue than teal. Basically, based on the design here,
So is it first cost?
This middle one.
middle one.
Oh,
This
the
one.
white,
Yeah.
no, this one.
Yeah. Basically, this should be red. This should be teal. This should be purple, actually. So.
Oh, so the blue in this picture is aluminum?
Yeah, the blue is aluminum, the teal is steel, the black is actually red, and it's associated with American cobalt magnets.
or projector is colorblind.
Very colorful.
So that the ACFT that has a weaker flow than the cusp.
Significantly weaker.
And the cusp.
And at the cusp as well, yes.
So is that so the ionization in this one is going to happen in the middle cusp?
Yeah, that is probably the case.
That's a good question. Good.
I'll have to find out. I'll have to read about it.